Ladies and gentlemen, welcome to the fourth series of geosynthetic webinar under the theme Reinforced Embankments on Soft Soils. This event is brought to you by the International Geosynthetic Society Chapter Indonesia or INA-IGS. My name is Rifa Nur Kayungyun, and it is a pleasure to act as your master ceremony in this event. Before we start, allow me to read the rundown of our event this afternoon. First, I will be reading the rules of the webinar. Second, there will be an opening remarks by the President of INA-IGS, Bapak Budianto Wijaya, PhD. After that, the event will be guided by Bapak Michael Dobi as our moderator to start the presentation of Kerry, Rowe. The event will then continue with a Q&A session. We would like to ask you to stay with us until the end of the event because we will be doing a quiz with a total of 250,000 rupiah for 2 winners. We will also give you access to the e-certificate at the end of this webinar. Ladies and gentlemen, for your own convenience, please put attention to the following rules. You can submit your questions for the speaker through the Q&A feature located at the bottom of the screen. The question should be in English. You can raise your question before, during, and after the presentation of the speaker. We expect you to stay with us until the end of the event to get the information you need regarding the e-certificates and also the soft copy of the presentation from the speaker. This event is also live streamed on INA-IGS YouTube channel, or you can directly go to the link s.id/INA-IGS04YT. If you have any question, please contact Sandy at the numbers shown on your screen or on the chat box. Now, without further ado, I would like to invite the President of INA-IGS, Bapak Budianto Wijaya, PhD, to give his opening remarks. To Bapak Budi, the time is yours.
Good afternoon, ladies and gentlemen. The Indonesian chapter of the International Geosynthetic Society welcome you to our fourth Geosynthetics webinar. Today, we are delighted to have the distinguished speaker, Professor R. Kerry Rowe from Geo-Engineering Center at Queen's RMC, Canada, to share his knowledge and experience to all of us with the topic of reinforced embankments on soft soils. We hope we find you all well and benefiting from this webinar. Thank you.
Thank you, Bapak Budi, for your kind remarks. Ladies and gentlemen, now this webinar will be guided by our moderator, Bapak Michael Dobi. Before I give the floor to Bapak Michael Dobi, I would like to remind you that you can start submitting your questions from now, during, and after the presentation by using the Q&A feature. You can also add comments or upvotes if there is a similar question as yours, or you just simply like the question raised. We would like to also remind you to stay with us until the end of the event to get the information you need regarding the e-certificates and also the soft copy of the presentation from the speaker. Now, please welcome our moderator, Bapak Michael Dobi. To Bapak Michael Dobi, the time is yours.
Good day, everybody. I hope that you can now hear me. If it's not working properly, I'm sure someone will come and tell me. I have a great honor and duty today, which is to introduce our speaker. This is for the fourth webinar in our series of webinars held in 2021 by the Indonesian chapter of IGS. In fact, before I do this little introduction, I'd also like to thank very much the people who organized this event, particularly to Rifa, to Sandy, and to Astri, and to a number of other people who work very hard to make these webinars so successful. Definitely without their expertise and help, we wouldn't be able to do this kind of event so smoothly. So thank you very, very much. So now I would like to spend just a few minutes telling you something about the event today, and in particular to our speaker, Professor Kerry Rowe. So there are a few slides coming up here, if we can go. Yeah, so here is the profile for our speaker. And as I begin to talk to you, you can start to read through some of the incredible achievements that Kerry Rowe has had during his career. And I would just actually like to highlight a small number of things, because I think some of these are very special. You can see affiliations he has, expertise he has, which is very, very wide, especially in the field of geosynthetics and related geotechnical fields. He's also delivered many important lectures during his career. And today is one of those occasions, because the lecture today has a special title. It's what's called the Mercer Lecture, which I will come to briefly in a minute. But I would like to mention a few special things. So after Kerry's name, if you look carefully, he had initials, and the first one was OC. And you might wonder what that is. Well, in fact, it's the Order of Canada. And I think this is the most incredible achievement, because it's a civil honor bestowed, well, I mean, the top of this order is actually Queen Elizabeth II, but it's bestowed on people in Canada who provide special services to the country. And I've managed to find the citation given to Kerry when this was awarded. So, and I'm going to read it, because I think this is something that is really inspiring for engineers. So let me read through the words there. And it says that Kerry Rowe is a passionate leader in the safeguarding of Canada's natural resources, a professor at Queen's University and a pioneer in environmental engineering. He is responsible for many of the designs, techniques, and materials now used to manage waste disposal in the developed world. His seminal research on landfills has led to critical advancements in protecting land and water from contamination. Renowned for his dedication to the advancement of this field, he has served at the helm of numerous professional societies and institutional committees. I think that's a really wonderful statement. And Kerry, I really honor you in achieving that kind of citation for this award. So let's move on to the next one. We haven't quite finished there with a few words about Kerry, because a couple of special things here. Perhaps when many of you were quite a lot younger, well, you were a lot younger, but even so young, you wouldn't have known about this. But in November 1992, in Indonesia, we had the inauguration, that's to say the beginning of INA-IGS, that's the Indonesian chapter of IGS. And you might be interested to hear that the IGS president at that time was a certain Dr. Kerry Rowe. And he attended that event. I remember meeting him there probably for the very first time. And he delivered a keynote lecture entitled Reinforced Embankments on Soft Cohesive Deposits. So quite interestingly close to today's title. But what was so nice about that was that Kerry was present at the start of our chapter. And he's come back today for his second visit to Indonesia. Sadly, he can't come in person today, of course, but he's come to us electronically. And we really do welcome you today, Kerry, to this event. And we're much looking forward to hearing from you again. Actually, his role in our region hadn't quite finished, because also in 1994, we had the Singapore International Conference from IGS, which I think would have brought the end of Kerry's presidency, because normally the president goes from international conference to the next one. So that's another occasion when he would have got very close to us, but not quite reaching Indonesia in that case. Now, the Mercer lecture, what's special about that? Well, Dr. Brian Mercer was a very interesting man. I was lucky to meet him early in my career in geosynthetics. You can see he also had some very prestigious awards, the OBE and also FRS. That's a fellow of the Royal Society. Sadly, he passed away quite a few years ago, as you can see. But amongst his many achievements, he was an inventor, basically, and he invented processes for manufacturing polymer meshes and nets for use in civil engineering, and eventually creating what we call geogrids. And here's a really incredible picture from the 1970s where he's meeting up with another gentleman there on the left, not on the far left, just the closer one, which is actually His Royal Highness Prince Philip. Sadly passed away just a couple of weeks ago. And in this particular picture, Dr. Mercer is explaining to the Prince the incredible strength you can achieve in polymers when you treat them in the right way. So in honor of Dr. Mercer, the Mercer Lecture Series was created in 1992, and many well-known geosynthetics people have spoken there, and the most recent one is Kerry Rowe. And I think I just want to read that last sentence because this is really important, that the key objective of the Mercer Lectures is to promote cooperation of information exchange between the geotechnical engineering profession and the geosynthetics industry. And I think this is the most important thing. And I think you'll find from Kerry's presentation shortly that that's exactly what's achieved. So I have, I think, one more little slide to show you, which is just a bit of fun, really. A lovely picture taken at another IGS event. This was actually 2 IGS workshops that were held in Munich in 2018. Sadly, the words have not come through correctly. It's still got the words from the previous one, but never mind. But let me just say, looking at that picture, this is really nice when people get together at these events and they exchange their knowledge and their expertise, and certainly the IGS workshops really were and still are extremely good events. Now, if you can look closely in that picture, you will see there are 3 gentlemen with white beards, and only 2 of them have been past IGS presidents. The question, of course, which one has not been? Now, this could be a question in the quiz later on. You never know. Is it the man on the left, in the middle, or on the right? In fact, what's rather nice in that picture, our speaker at our webinar 2 months ago is also in that picture, and that was also, and of course, what's interesting is that Kerry and Richard both live in the same place. They're in slightly different universities, but in the same place in Canada. So I think that should hopefully give you enough to start off with. I need to stop my bit now and invite Kerry to speak to us. So we're looking forward to this presentation. Kerry, thanks very much for getting up so early today to deliver this to us. And the floor is now yours.
Thanks very much, Mike. Hopefully you can hear me. Somebody just tell me that you can hear me.
I can hear you, yes.
Excellent. So thank you very much for that very kind introduction. It's really a great pleasure to be back with the Indonesian chapter after 28 years since the formation, and I was in Jakarta for its formation. So here we are, 28 years later, and I'm going to be sharing with you some thoughts on geosynthetics aiding construction on soft soils. And it's a great pleasure to be following my colleague, Dr. Richard Bathurst, who talked about walls. And we are, in fact, in the same Geo-Engineering Centre at Queen's RMC. So let us begin. And as Mike has already indicated, this lecture is the Mercer Lecture, and it is in honor of Dr. Brian Mercer, who is the inventor of modern tensor geogrids. And you'll see them appearing every now and then in my presentation. Ladies and gentlemen, over the next 50 to 55 minutes, I would like you to join me on a 40-year exploration of the use of geosynthetics to aid construction of embankments on soft and/or difficult soils. And by the end of this talk, I hope to have left you with 3 key points. First, soil reinforcement is well established as a cost-effective alternative to or augmentation of traditional construction methods. Second, in the design of embankments on soft soils, reinforcement can play a key role, and understanding its properties and characteristics is critical to the success. But also, while geosynthetics are very useful, they are not magical. They obey physical laws. And as with all engineering materials, we need to design properly. Thirdly, while geosynthetic properties and characteristics are important, we must not get so absorbed in the geosynthetics that we forget the soil mechanics. It too is an essential consideration for ensuring good long-term performance. My topics today start fairly simply and then build up in complexity, with the objective leading to the final topic, highlighting that current research into pile-supported embankments needs to pay more attention to the lessons from the past 40 years that I'll be presenting to you in this lecture. So let us begin where I began 40 years ago, building reinforced embankments on peat. For those of you not familiar with peat, and I'm hoping you can see my pointer, we see it here. Perhaps you can't. Okay, looks like that's not working. So peat is an organic material. It is usually submerged, otherwise it will generally begin to decay. And it has a relatively low submerged weight. And since the strength of soils, including peat, is given by the Moore-Coulomb criteria, which involves the effective stress and a friction angle, if you have low effective stress, you have low strength. And when we're building on a peat deposit, a very important consideration is ensuring the rate of construction is such that we do not have too much excess pore pressure. And one of the ways of representing excess pore pressure, delta U, is in terms of parameter B bar, which is the ratio of the excess pore pressure generated by a change in total stress, delta sigma V. And so we want to make sure that we are getting an increase in effective stress to get an increase in strength to maintain stability. So we're going to talk firstly about an embankment on a relatively thick peat deposit. It's just under 7 meters thick. And it was reinforced with a woven multi-filament tier textile, and its properties are shown on the screen. And in this case, the peat was underlain by a fairly good foundation, a firm sand. And our objective was to get an embankment 1 to 1.5 meters above grade. Now, peat is a very compressible material. This material had an average water content of just under 800%. And so it was built in stages. And in stage 1, we placed 2.74 meters of fill. And after that had just been placed, we had 2.6 meters of settlement. So were about 14 centimeters above the original ground level. The maximum strain in the reinforcement at this time is 5%. We then left the embankment for 8 months for consolidation and strength gain. And when we came back 8 months later, our 2.74 meters of fill had given a rise to 3.1 meters of settlement, which means we're actually below where we started. And as you can see in this schematic, we are below the water table. And as you can see in this photograph, much of the embankment was indeed below the water table at this point in time. We then placed the second layer of fill. And before I get to that, I should comment on the reinforcement and how it had changed. And the strain had dropped from 5% to 2%. Why had the strain dropped? Because over the 8 months, as the soil consolidated, as the pore pressures dissipated, the effective stress increased, and therefore the strength increased. And now the reinforcement didn't have to work so hard. Now, this is a common characteristic of soils where pore pressures dissipate after the end of construction. The reinforce is most critical at the end of construction, and it becomes somewhat less critical with time. As we'll see later, that's not always the case. So here we are in stage 2. We've placed additional fill. So we've now placed 5.9 meters of fill. We have 4.2 meters of settlement. So we're actually now 1.7 meters above the original ground level. And our maximum strain has increased to 11.5%. Now we leave it for another period of settlement. And we come back 2 years later. And our maximum strain has dropped from 11% to 8%. Our settlement has increased to 4.8 meters. So we're now 1.1 meters above original ground level. But again, you'll see that with the pore pressure dissipation, the soil gains strength, the reinforcement strain decreases and it becomes less critical. Much of the reinforcement, as we'll see later, is time dependent. And so the time dependency of the reinforcement is not particularly critical in this situation because the strain is reducing with time as the soil gains strength. So to summarize, in this particular case, a high modulus geotextile served to reduce lateral movements and increase stability. But it does not come equipped with skyhooks. If you're going to get large consolidation settlements without reinforcement, you will still get large consolidation settlements with reinforcement. A very important consideration was controlling the rate of construction so that the excess pore pressures never gave a B bar greater than 0.34. In other words, the excess pore pressures were always less than 34% of the change in total stress due to the new fill that had been placed. And effective deformation and strength parameters provided very good agreement between calculated and observed behavior. Peat is a frictional material with a cohesion intercept due to the tensile strength of the peat. Now, that was a case where the peat was quite thick, but was underlain by a firm stratum. Let's go to another case where the peat is not so thick. It's less than 2 meters, but it's underlain by very soft organic silt, whose underend shear strength is only 4 kilopascals just below the peat and increases with depth. And again, our objective was to build a 1.3 to 1.7 meter granular embankment above grade. And in this case, we used a polypropylene biaxial geogrid the properties shown here. And this is the type of material that was invented by Dr. Mercer. And here you can see the geogrid ahead of the fill. And you can see that even as the fill advanced, the geogrid is in tension. And in fact, the underlying peat has experienced a tension crack. Here you can see the fill advancing over the peat. You can see the reinforcement being placed, and this photograph is an instrumented section. And you'll notice the piles of fill that the contractor has placed. Where they are at the moment is not problematic because that's just before the peat begins. But that turns out to be problematic if they do that over the peat. We don't have time to go through all the results, but let's just summarize the key findings. And a key finding from this case was that the control of the rate of construction was again critical to short-term stability. The embankment was stable whenever the value of B bar was less than 38%. So the change in pore pressure was less than 38% of the change in total stress. And that was part of the specification. But at one point, the contractor got a little enthusiastic and piled up one of those big piles of fill, which very quickly forced B bar to 0.7. And guess what? If you don't follow the specifications, you have a problem, and a local failure occurred. This really reinforced the importance of controlling the rate of construction on peat material. So with the benefit of case histories like this, which validate numerical analyses, design charts were developed, and one such chart is shown on this slide. And on the left-hand axis, we have the unit weight of the fill to be placed plus the height above original ground level we want to achieve. And then we have curves for different depths of fibrous peat. And on the bottom axis, we have the geosynthetic tensile stiffness required to get good performance, provided you keep the excess pore pressures below 34% of the change in total stress. And you can see here that if we wanted to get a 1.5 meter embankment at 20 kilonewtons per meter cubed, that gives gamma H of 30 kilopascals, we wouldn't need very strong reinforcement on 3 meters of peat when it's underlain by a firm foundation. But when we get to 5 meters of peat, we need about 400 kilonewtons per meter in terms of tensile stiffness. And when we get to 8 meters, we need about 800 kilonewtons per meter of tensile stiffness. So the stiffness of the reinforcement is an important characteristic. This design chart is for peat underlain by a firm stratum, but similar design charts have been published and are still very useful today for peat underlain by a soft soil, which is also a very common situation. So let us now move from peat to soft clay soil. And here we are in the Netherlands with the Aalmeer test embankment, which was a 3.3 meter thick layer of organic clay, relatively low underhand shear strength, and 2 test embankments were built. In each case, a trench was excavated and used to form a retaining bank. Then hydraulic fill was placed until failure occurred. And you can see photographs at the bottom. On the left, just after excavation of the trench, and on the right, just before onset of failure. You can see where the bulging is occurring. And then in the next photo, you can see it has pretty well unquestionably collapsed. Now that was the unreinforced section, and it failed at 1.75 meters of hydraulic fill. The reinforced section was essentially identical, except that a layer of multi-filament woven geotextile was placed on top of the organic clay, and the retaining bank placed on top of that, and then the hydraulic fill was placed, and it failed at a height of 2.75 meters. With that significant difference due to the relatively high strength, high stiffness reinforcement. Now, if we start with the simple case of the unreinforced embankment, if we do a traditional limit equilibrium analysis or a traditional finite element analysis, we get the same result. The failure occurred due to the development of an uncontained plastic zone with a failure mechanism that passed tangent to the firm base and through the toe of the trench. And it failed at a 1.8 meters. Now let's look at the reinforced embankment, and at the failure height for the unreinforced case, we have contained plasticity at 1.8 meters. So the reinforcement is already carrying some of the shear stress. It's carrying some of that load. And so the soil is maintaining its strength for a longer period of time. But that can't last forever. And when we get to a height of 2.05 meters, we now have uncontained plasticity. And all that's holding the embankment together now is the reinforcement. So let's look at what happens to the reinforcement. And we're plotting on the left-hand axis the embankment height, and on the bottom axis the increase in strain in the reinforcement at point A, just at the edge of the retaining bank, the inside edge. The white line here is the calculated strain, and the white circles are the observed strain. And you'll see that up to a meter in height of the hydraulic fill, we do not see any significant strain in the reinforcement. And the reason for that is quite simple. At this amount of fill, the soil is still behaving effectively as an elastic material. And it can control the load. It can sustain the shear stresses induced by the load without any difficulty. But as we go over 1 meter, we now start to induce shear failure within the subgrade. And as the plastic zone begins to develop, the reinforcement starts to take load and its strain increases. At a height of 2.05 meters, we now have uncontained plasticity. Now it happens that this is the height corresponding to a working height with a factor of safety of 1.3. And if we look at our strain plot, you can see that our strain is about 1%. This is fairly typical of reinforced embankments on soft soils, who are traditional soft soils. And you'll see that the strain in the reinforcement is relatively low because we are typically just about the limit of what the soil can carry with a factor of safety of 1.3. And so, yes, the reinforcement is doing a bit of work, but it's mostly there giving you the factor of safety. And as we saw with Peat, if we monitored the strains in this reinforcement, they would decrease with time with pore pressure dissipation if we'd left it at the working height. In this case, it wasn't left at the working height. Additional fill was placed and eventually failure occurred. And it occurred at a strain of about 3.3%. Now, this reinforcement can sustain a strain of up to about 10%. So why did it fail? And it fell because of pullout of the reinforcement between the retaining bank and the underlying organic clay at about a third of the load it could sustain. So this illustrates that while the stiffness and strength of the reinforcement is important, anchorage is also important. Now let us consider the situation where we can't build our embankment to the height we would like just using basal reinforcement. So now we need to also increase the strength of the soil during construction, just as we had to do on peat. And for clays, one of the best ways of doing that is using prefabricated vertical drains, or PVDs. So we're going to use reinforcement as a basal reinforcement and PVDs together. Now, PVDs have been around for a long time, and they have proven to be very successful at aiding in construction on soft and difficult soils. A paper published just a few years ago looked at 4 cases with embankment heights of 5 to 11 meters on soft clay, up to 12 meters thick, using reinforcement with a relatively high tensile strength of 1,000 kilonewtons per meter, and PVDs in a triangular spacing. And what this study showed is that to get the heights that were required in these embankments, neither reinforcement nor PVDs alone were sufficient. But by using them together, we get the combined benefits of both. The reinforcement and the PVDs together increase the safety factor by 50 to 70%, depending on the particular case. With the reinforcement increasing stability and allowing more fill and more consolidation and strength gain at any given time, while the PVDs accelerated settlement. But as before, reinforcement will not get rid of consolidation settlement. Just as in the case of peat, if you're going to get consolidation settlement without reinforcement, you're still going to get it with PVDs and reinforcement. But the PVDs and reinforcement give you a way to manage that consolidation settlement. The PVDs provide a rapid reduction in excess pore pressures and hence significant quick strength gain. So let's look at some analyses of embankments where we're using PVDs and basal reinforcement to get an idea of the significance of the reinforcement stiffness. And here on our left-hand axis, we're plotting net embankment height. That's the total fill thickness minus the settlement. So it's how high we are above original ground. And we're plotting it against the embankment fill thickness. And all of these cases have got PVDs in a arrangement, as you see shown here, at a spacing of 2 meters. We're constructing at 2 meters a month. The rate of construction is important because we're trying to get some strength gain during construction. And we can see that with it unreinforced, we can get to just over 2 meters before it fails. If we put in reinforcement with a stiffness of 250 kilonewtons per meter, we really don't gain very much. At 500, we can get to about 3 meters. With a stiffness of 1,000, we're getting up to over 4 meters. With a stiffness of 2,000, we're getting to about 6 meters, but we're still going to get about 3 meters of settlement. So we've got 9 meters of fill to get 6 meters above grade. So let's now move from what I would call traditional soils. These are soils that are characterized by a maximum excess pore pressure at the end of construction. And after construction is complete, the pore pressures dissipate and the soil gains strength. And so the reinforcement is most critical to get us to that end of construction point. And after that, the soil plays a larger and larger role. As I say, that is a common situation, but it's not always so. So now we're going to move to a little bit more complicated case of a rate-sensitive clay. You could, of course, argue that all soils, and particularly clay soils, are rate sensitive, and you would be right. But some are especially rate sensitive. And the rate sensitive soils I'm going to be talking about are characterized by the fact that after the end of construction, the pore pressures continue to increase and not decrease. In about a third of the cases examined by Crooks et al. For embankments constructed in Canada, they were on soils that I would describe as rate sensitive. In other words, after the end of construction, the reinforcement continues to be important because the soil is losing strength as the pore pressures increase. So let us look at an embankment that we constructed. We both constructed an unreinforced and a reinforced section in the province of New Brunswick in Canada, who have a particular problem that the Department of Transportation would build embankments and they'd feel pretty pleased with themselves. And a month or two later, the embankment would fail. And the reason was rate-sensitive soil. So we wanted to see how reinforcement could aid on these soils. Now, the properties of the soil are shown on this slide. The property I particularly draw your attention to is the liquidity index. And one of the characteristics of these rate-sensitive soils tends to be a liquidity index of around 1. In this case, a woven polyester geotextile was used with a strength of 220 kilonewtons per meter, and most significantly, a failure strain of 13%. And we constructed the reinforced embankment without any difficulties to 8.2 meters, and we left it. And after a period of time, it failed. You'll notice that at the toe of the stroke, there's a fenced off period, which is where the area where we're monitoring, which was originally at the level where I'm standing taking at this photograph. But at the time I've taken the photograph, it's heaved up 2 meters because of a failure that occurred after the end of construction. So embankments on rate-sensitive soil, and in particular this one, exhibit a viscous type failure, and it creeped to failure after the end of construction. It was characterized by deformations and excess pore pressures increasing after the end of construction. And a failure occurred at the critical time when the pore pressures increased sufficiently that the shear strength could no longer sustain the shear stresses due to the weight of the soil. One traditional method of getting shear strength on soft soils is the field vane. And many years ago, correction was published by Byram based on the plasticity index. But even if you apply that correction, you still overestimate the shear strength on these rate-sensitive soils. The reinforcement did serve a significant role. It increased the failure height and reduced the viscoplastic deformation. So it doesn't get you away from having rate-sensitive soil, and you still have to be especially careful, as we'll see in a moment, but it does help. So let's see what happens in this case with the strains in the reinforcement over time. So we're going to look at an embankment on a rate-sensitive soil at working load with a factor of safety of 1.3 based on the field vane with a traditional correction and a design strain in the reinforcement of 5%, which is fairly traditional. And the embankment height is 6.75 meters. And on the left-hand axis, we're plotting the reinforcement strain and we're plotting it versus time. And after 500 hours, we're just exceeding the 5% design strain. At the end of construction, we're at about 6% strain. So far, so good. But now, as we watch with time, and just as we saw in the Sackville embankment, the strains don't decrease as they did on our previous examples, they increase. And if this reinforcement had a failure strain between about 11 and 13%, we would expect a failure to occur between 12 and 21 days after the end of construction. And that is indeed the sort of thing we saw at the Sackville embankment. If the strain could sustain, if the reinforcement could sustain a strain in excess of 16%, then we would come to an equilibrium. So what this illustrates to us is that if we have a rate-sensitive soil in the context I'm talking about, we need to pay much more attention to the reinforcement to make sure it can sustain the strains for the critical case post-construction when the excess pore pressures reach a maximum. Now, it would take a good 1 hour lecture to talk about how to do that, and we don't have another hour. So if you are interested, I refer you to our 2002 paper in the ASCE journal. Now, we've discussed viscous soil, but we can also have viscous reinforcement. I mentioned before that this is not especially critical on traditional soils. We need to think about it, but it's going to be particularly important, as we'll see, on rate-sensitive soils. So here we are plotting net embankment height again, so fill thickness minus maximum settlement, against the long-term design reinforcement strain on a rate-sensitive soil with a rate-sensitive reinforcement G1. And in this case, we're going to begin constructing at a rate of 10 meters per month. And if we have a design reinforcement strain in the long term of 3%, we could get to a height of 2.9 meters. If we increase that design strain to 5%, we could get to 3.04 meters. Now, if we were to change the rate of construction, it becomes important. And you can see that for the same design strain of 3%, we could now get to 3.1 meters. So it's important, this rate of construction is important with respect to both the rate sensitivity of the soil and of the reinforcement. Now let's look what happens if we change the reinforcement. So we initially looked at one with a relatively high rate sensitivity, and now we're going to look at one with a lower rate sensitivity. And on the case with the higher rate sensitivity at 10 meters per month, we could get to 3.04 meters. At the same construction rate with a lower rate sensitive reinforcement, we get a 12% increase to 3.4 meters. So on these rate sensitive soils in particular, we also need to think about the rate sensitivity of our reinforcement. Again, getting into the design details would be an hour lecture in itself, but if you are interested, I refer you to this paper in Geotextiles and Geomembranes. We're now entering the latter part of the talk, where we're going to talk about floating column supported embankments. This and column-supported embankments are hot topics at the moment. They're a focus of quite a lot of current research. And I'm going to try and get you to think about these problems, which are really being considered largely on the basis of traditional soil mechanics, in terms of some of the issues we've just talked about. So let us begin on the simplest case with a column-supported embankment with and without geosynthetic reinforcement. So here you see the columns. They could be piles, they could be deep mix columns, and where the reinforcement would lay is above the top of the columns or piles as part of a load transfer platform. And then above that, we have an embankment. A number of full-scale embankments were constructed in France a few years ago and analysed by us. And there was one without piles or reinforcement, one unreinforced pile-supported embankment, and one with geotextile reinforced and pile-supported. Because of time, we'll only look at the latter two. And here is some settlement information for the case where no geotextile was used. And the settlement just above the pile was 9.9 millimeters. And between it, it was 131 millimeters. So our difference is 121 millimeters. Now what happens if we put a reinforcement above the pile in the load transfer platform? Our pile head settlement increases to 31 millimeters, but our subsoil decreases to 78. And our difference is less than 50 millimeters. Why? Because the reinforcement is helping transfer load from the subsoil directly between the piles to the piles themselves, and hence make more effective use of the piles. Now, just as before, reinforcement and piles on their own may not be sufficient, and we may need to get the soil to gain additional strength during construction. So we bring back our PVDs. And here is a layout involving deep mix columns, is to the circles, and PVDs, which are the rectangles, obviously not drawn to scale. And we're going to look at the performance of a cross-section through this system. We're focusing on 2 points, A and B, halfway between two deep mix columns. And point A is at the bottom, point B is at the top. We're going to be particularly interested in the settlement at point B and in the strains, in the pore pressures at point A. So let us now look at the excess pore pressures at point A on the left-hand axis versus time. And we're looking at the case without PVDs shown in yellow and with PVDs shown in blue. And at the end of construction, there's a little bit of a gain with PVDs in this case, but not all that much. But you see a big difference in the 3 months following construction. So without PVDs, our excess pore pressure is about 70 kilopascals 3 months after the end of construction. And it takes about 7 years before those pore pressures dissipate. With the PVDs, after 3 months, we're down to about 23 kilopascals pore pressure, and most of the settlement has occurred in the passage of about 1 year. So there is a big effect of the PVDs. There's also an effect in terms of settlement. You can see that without PVDs, it gets a settlement of about 0.6 of a meter, and as I said before, about 7 years to reach that settlement. But with the PVDs, there's 30% less settlement due to the strength gain in the soil and less undrained deformation. And most of the settlement has occurred in a year. So here, reinforcement, the deep mix columns and the PVDs are all working together. Next, let's consider viscosity of the reinforcement. So here we're plotting the maximum tensile strain in the reinforcement versus time. We're on a soil which is rate sensitive. We're constructing at a rate of 10 meters per month. And we're plotting here for a rate sensitive reinforcement G1. We met that reinforcement earlier. And at the end of construction, our strain is 4.5%, which is a fairly typical maximum value, typically designed for a maximum value of about 5% strain. But in this case here, you see the strain continues to increase until about 8%. If we had rate insensitive reinforcement, we still get creep of the subgrade, but we get to a strain of about 7%, with the difference between those being the creep strain within the reinforcement itself. If we do a pure creep test at the load corresponding to the end of construction on this reinforcement, we get slightly more strain than actually is occurring in the embankment situation. Why is there a difference? Because of redistribution of stress that occurs in the embankment situation with consolidation. Now, the flip side of the increase in strain with time and creep is relaxation of force on a rate-sensitive soil. So now we're looking at exactly the same problem, but we're looking at the tensile force. And we're starting off assuming that the soil is still rate sensitive, but the reinforcement is elastic. And we're taking the same stiffness as for the rate sensitive reinforcement at the end of construction. And so at the end of the construction, our force is about 60 kilonewtons per meter. And because of the creep in the subgrade, we increase to around about 90 kilonewtons per meter in this particular case with an elastic reinforcement. With our rate sensitive reinforcement, we have the same load at the end of construction, largely because the stiffnesses were selected to be the same. And we're at about 80 kilonewtons per meter. Why the difference? Because of relaxation that's occurred in the reinforcement. So that relaxation goes along together with the creep strain and more deformation. If we did a pure relaxation test, this is what we would predict for that reinforcement. And again, in isolation, you get more relaxation than you would in the real situation due to stress redistribution. So stress relaxation tests, just like creep tests, provide useful data for use in soil structure interaction analyses, but do not directly indicate what will happen in a soil structure interaction, which is what we have in this particular case. So we're now moving to the very last topic, and that is end-bearing column-supported embankments. This is much the same as we saw before, except now the columns extend down to a firm stratum. We are going to look at the reinforcement on top of the columns, which will take up a deformed shape, we can imagine, similar to shown in yellow. And what that will do is at the column, we will have a load above the column A due to the weight of the soil above the column, but the additional load transfer to the column by the reinforcement is a load B. So the column is going to be carrying both load A and B. A directly above it, and B due to the load transferred between columns by the reinforcement. If we go to the reinforcement halfway between the columns, we have a load B plus C acting on the reinforcement due to the weight of the soil above it, with portion of that load B being carried by the reinforcement to the columns, and a reduced load C actually carried by the subgrade. Now, a very important part in this load transfer is soil arching. And if we go back to Terzaghi, 1943, he said arching is one of the most universal phenomena encountered in soils in both field and laboratory. There are numerous models around for analyzing the problem that I've just been talking about. And as I say, this is a very hot area of research. If you pick up an issue of geotextiles and geomembranes, chances are you'll find one or two or perhaps even more papers on the topic in every issue. They assume the shape of the failure surface with soil arching. Note the word assume. And many assumed failure surfaces lack a sound theoretical basis. They're based on data, often laboratory data, for a limited range of conditions. And that's fine for analyzing the situation for which they were obtained. But they're being used too generally. Now, soil arching itself is a complicated thing. It is a deformation-dependent process. And the deformation is described by the reinforcement sag. And that may or may not agree with what is assumed. The observed behavior may or may not agree with what is assumed in most of the existing analyses. And that all depends on strain compatibility. So serviceability-based design must depend on the time-dependent, coupled, arching, stress, reinforcement, deformation behavior. Now that is quite a mouthful. It actually brings together everything we have been talking about in the presentation today, going back 40 years. Previous studies typically assume that the maximum height of the failure surface is equal to the critical height. The critical height is the point in the embankment where you don't get differential settlement. And that's the objective of all of this, is to minimize differential settlement at the surface of the embankment. Unfortunately, this assumption doesn't always match observations. And the explanation's fairly simple. The failure surface is a zone of high distortion. It's unlikely to be a plane of equal settlement. So here you can see the failure, which is shown by the lines, and the failure surface is shown by HFS up at the top of the red zone. And the critical height is shown well above that. So the critical height, the point at which you don't get differential settlements at the surface above that line, is related to the failure surface height, but is not equal to it. So to design for a maximum arching, we need to ensure strain compatibility. The reinforcement stiffness to generate the maximum arching stress condition must sag just enough, but not too much. Thus, while reinforcement must have sufficient strength It must also have the right stiffness. Again, we come back to stiffness. Yes, strength is important, but so is stiffness. Serviceability assessment of embankments after construction, and we're talking here about serviceability, deformations under working conditions, are often based on limit equilibrium arching models. But of course, limit equilibrium models are deformation and time independent. They are indeed very useful for ultimate limit state assessment. But you can't expect a model that doesn't consider deformation and time to be suitable for a serviceability analysis when you have significant time-dependent characteristics. Also, short-term performance is not a good guide to serviceability assessment. Some of these things take years to develop. And the bottom line here, and the message I want to leave you with, is that we need to pay more attention to longer-term deformations due to soft soil creep and reinforcement creep relaxation in the design of these embankments. So we've now been on a journey over 40 years from what we were learning 40 years ago to current research. And my key points from this presentation are that reinforcement only plays a significant role when there's significant mobilization of shear strength in the foundation on a soft soil. The combined use of bearing capacity and limit equilibrium tends to work well for the ultimate limit state. But care is needed if you have a rate-sensitive soil. Plant element models, which are now very widely used, can model the observed behavior and provide insight regarding behavior, but have to be used carefully. Garbage in, garbage out. Embankments on peat are still something we have to deal with. Peat's been around for thousands of years, and we often need to build over it. Reinforcement is very useful. It reduces lateral movements and increases stability, but it will not prevent large consolidation settlements. We need to design to accommodate them. We need to ensure that the pore pressures are kept in reasonable bounds. Typically, excess pore pressures less than 34% of the change in total stress. And that means controlling the rate of construction. And effective deformation and strength parameters combined with pore pressures provide very good agreement between calculated and observed performance. Rate-sensitive soils, we can see the strain increase significantly after the end of construction in these soils. For a given embankment height, stiffer reinforcement can reduce creep in the foundation. The most critical time with respect to stability is not the end of construction, but sometime after the end of construction, when the maximum pore pressures are reached. And strength from laboratory and field tests need to be adjusted to take account of the critical stage, which occurs after the end of construction. For floating column supported embankments, the inclusion of basal reinforcement significantly reduces subsoil stress and decreases settlement, particularly differential settlement. Reinforcement and PVDs work effectively to give us less long-term crest settlement and horizontal movement by reducing the undrained deformation. Stress relaxation tests provide useful data to incorporate in more sophisticated models, but they don't tell us what's going to happen. For end-supported embankments, despite the advances that have been made in recent years, are still challenging. And the challenge is to ensure long-term serviceability requirements. And to do that, we need to go back and look at what we've learned over the last 40 years about rate-sensitive soils and rate-sensitive reinforcement. Now, this lecture has obviously provided a very compressed summary of a huge amount of literature over 40 years, based on field cases, on sophisticated lab tests, and advanced numerical modeling. And what it has all reinforced are the three key points I started with. Soil reinforcement is an established, cost-effective alternative to or augmentation of conventional construction methods. But we need to understand the properties of the reinforcement and take that into account when we design. And let's not get so caught up with the reinforcement that we forget the soil mechanics. This lecture is sponsored by both ISSM-GE and the IGS, and its purpose is to draw together the concepts of soil mechanics and geosynthetics. And it's also sponsored by Tensar International, who sponsors the Mercer lecture. And I'd like to acknowledge many of those who have contributed to the work that I have talked about today. And I thank you for your attention.
Wow, Kerry, thank you very much for that really excellent presentation. I think almost certainly there are at least 7 more webinars on each of those topics to expand on that, but we'll let you rest for the time being. I've been observing the questions as they've been coming in, and there are some very good ones. There are some which are slight repeats of each other, but I don't think that matters too much. Can you see the Q&A thing in the middle at the bottom of the screen? Because if you click on that, they should open up down at the bottom.
Okay, yes, yeah, well, actually it's the top for me, but
top for you. Okay, so it currently has 12 of them,
right.
And in reading through, I think if you can scroll to the top, as I said, I've been reading through these, and I suggest rather than me read them out, I think you can, if you go down and have a look for yourself. But I think a lot of very good questions here, and I think some of the answers to these will produce some additional information to supplement what you've been talking about over the last hour.
Yes, so the first question I see is, to reduce the settlement, could we install geotextiles in several layers, not only at the base? Is that the question I'm answering?
Yeah, if you have any comment on that, that would be great.
Yeah. Yes, just to be clear, when I'm talking about basal reinforcement, I'm simply talking about reinforcement near the base. It doesn't have to be one layer of reinforcement. So if, for example, we don't have sufficient stiffness or strength with one layer of material, we could have 2 relatively closely spaced layers of reinforcement. There would be a layer of fill between them. Obviously, because we're dealing with a bending situation, we need to keep the reinforcement towards the bottom of the embankment. We're not talking about reinforced walls as such here. That's what Richard talked about 2 webinars ago. But yes, absolutely, you could have 2 or even 3 layers of material with typically a bit of soil between them, a practical from a construction perspective, layer of soil between them, and that will serve to allow you more stiffness and or strength depending on what you need. So shall I move to the second question?
Okay. I mean, maybe I'm prepared. I'm going through them before you've got there. So let me. So
go ahead.
her one here. Yeah. So says, are there any methods that recommended to solve residual settlement problems. I don't know exactly 100% what he means by residual settlement problems, but related to the use of geosynthetics on embankments on soft soils.
Okay, so I'm going to assume by residual he's talking about secondary compression, creep, longer term creep deformations. And yeah, that's something we do need to consider, particularly on soils that are rate sensitive or quite creep dependent. Peat is also a good example of that. I focused on short-term performance of peat, but what I didn't tell you about in talking about that case is that we actually place more fill in a third lift that I didn't get to effectively overload the peat, and the reinforcement allowed us to do that. We left it for a period of time and then removed some of that fill. And what that does is it takes up some of the secondary compression that would have occurred over time. So stage construction and overloading is one technique that can be used to try and deal with what I'm assuming you're talking about, those residual or longer term secondary consolidation settlements.
Kerry, I think you're right there. I think that absolutely right. Now the third one, very good question, I think. This is from Gautama Santosa. During construction, should the contractor install instruments to determine B-bar? And what kind of instruments should be installed? Yeah, very good question.
Yes, I think it's an appropriate thing to do if it's an important embankment for you to have it instrumented. And basically the instrument you predominantly need is a pore pressure measurement. So you need some piezometers, depending on your particular system, and I guess your taste. You may select your piezometer, but these days often vibrating wire piezometers are commonly used, and you can monitor the pore pressures with time and monitor the amount of fill that's being placed.
Yeah, very good. Yeah. Now there's unfortunately this jumps sometimes, so I lose track of where exactly we've got to. Yeah, this one here. So from Mohammed Hamza. Yeah, this is not directly on the topic, but interesting. You might have a comment to make. It says, in the case of soil liquefaction, could we use geosynthetics to help mitigate the issues of liquefaction?
Well, I don't think what I've been talking about today is particularly going to help with liquefaction. If you want to really deal with liquefaction, I think you've got to deal with the root issue of the soil. What reinforcement will do is redistribute stresses on that soil, but it's not going to alter the fact that if you get an earthquake, that you're still going to get excess pore pressures that could cause liquefaction. So I really don't think that is the solution. In terms of pore pressure dissipation, to some extent, PVDs could provide some help, but I don't think that they alone either are a solution to liquefaction.
No, I think that's a good answer. I mean, I think just as a interesting extra comment from myself, in New Zealand, a lot of good work was done following the Christchurch earthquake, when there was a lot of liquefaction, and certain geosynthetic techniques were looked at and have been very successful, but that's definitely a different topic. We have another question about measuring B-bar. That's the same, so we'll move on. About the LTP, what about the controlling parameters? What's really important? Height of embankment, distance between columns, or thickness of the soft soils? I think that's a good question as well.
So can you just read it again?
Yeah, so about LTPs, what is the most important controlling parameter? The height of the embankment, distance between the columns, oh, and it's jumped again, so I've now lost it, or the thickness of the soft soil?
Oh, this is a multiple choice question I don't want to answer because I think they're all important.
Exactly.
I want point D, all of the above. I don't think we can say that any one of them alone is the critical issue. I think all of them are very important, and you've got to think about how they interact.
I think there are some fairly important geometry requirements that need to be looked into. Yeah. There are some famous cases I'm aware of, for example, in Malaysia, referred to as the mushroom problem, when basic requirements on spacing compared to thickness of fill were wrong, and unfortunately you just end up with a load of bumps, big ones, and yeah, I think that's true. We need to look at everything there. That's the B-bar question again. We have another question there about using 2 layers rather than 1. We've already answered that one, or you have. Now this one. What is the range of sensitivity of a soft clay which is usually found critical for doing ground treatment? What type of ground treatment is found suitable for highly sensitive soft clays? Please discuss. Well, that sounds like another webinar, Kerry.
Yes, it is indeed. So we've got to distinguish what we mean by sensitivity. To some people, a sensitive soil has got a sensitivity of 6. To me, that's not a very sensitive soil. If you get to an extremely sensitive soil, like a leader clay, which has maybe a sensitivity of 60, 80, 100, then reinforcement has its challenges. We've looked at that. There have been field trials and we've done theoretical analyses on it. And for these very, very sensitive soils, and I'm assuming that that's what the question is about, then you need so much stiffness in the reinforcement to prevent it beginning destructurization, which is a breakdown in the overall structure, that you have difficulty really making a place for it with the reinforcement. Now, that's a very special case. If you're talking about a soil with a sensitivity of 5 or 6, then I think all that I talked about today is relevant. The Sackville embankment that I talked about would have a sensitivity a little bit more than that, but within that range. It's not a soil that is like the leader clays, which completely destructure and effectively become a liquid. And a good clue to that is the liquidity index. So that if you have a liquidity index well above 1, so its natural water content is well above the liquid limit, that's a pretty good warning that you have a very sensitive clay. If you have a liquidity index around 1, or a bit more than 1, perhaps just a little less, then you are dealing with what I would call as a rate-sensitive clay, in that the pore pressures will definitely build up after the end of construction, but you can still get a significant advantage from reinforcement. So it's only in the very extreme case of a leader clay, as we have in Quebec and parts of Ontario, as you have in Norway, their reinforcement struggles. But for your traditional sensitive clays, they can be very beneficial.
Yeah, thanks. I think the case here, Kerry, assuming people are talking about Indonesian conditions, we don't have the super sensitive quick type clays like Norway or Canada. We have Holocene marine clays, which probably would have a sensitivity from vein testing in the order of 4 or 5, and I think very relevant. But no, we haven't had the geological history that creates the quick clays here. So certainly it's not the super sensitive soils as you mentioned.
In which case,
okay,
everything
we have
I said
next
today
question.
is relevant.
Exactly, that's the whole point. Yeah. So this is from Harry Tai. He says, "Thank you for the very excellent presentation." I certainly echo that comment. So usually, strength of geosynthetics increases the safety factor of an embankment using the geosynthetics. However, in your study, it shows safety factors increasing a lot if stiffness of geosynthetics increases. Can you explain a bit more about this? Thank you very much.
Okay, so obviously the strength of the reinforcement is important because of the load it has to carry. So you need more strength than there is load to be carried. But stiffness is often underappreciated as important. Why stiffness is important is it reduces the strains in the soil, and that reduces the plasticity. The stiffer it is, the more likely the reinforcement is to attract load to itself and take load from the subsoil. And where it's particularly important as you get more and more sensitive in terms of the soil, and you get rate sensitivity, then it becomes quite important. And as I said, you get to the point in the extreme case where you just can't get enough stiffness. But for most cases, stiffness is a very important consideration because it helps reduce the shear stresses in the soil by attracting the load to the reinforcement. There is a strain compatibility issue here. And as we know, most soils lose some strength as they strain. And what you'd like to do is keep those strains so that you maintain your peak strengths and you don't start running down a post-peak curve in your soil.
Yeah, I think the word you mentioned there, the compatibility issue is a really important one, and so very, 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 very stiff doesn't necessarily give you the performance you want. You've got to get that right, I think. But likewise, also very, very soft also wouldn't. So compatibility important.
Exactly, as I pointed out, in some cases you don't need very much stiffness at all. In other cases, you need a lot of stiffness. It all depends on the nature of the soil, the stiffness of the soil itself, and also things like the thickness, for example, in the peat example.
Yeah. Okay, there are a couple of questions which are repeats on multiple layers and the B-bar measurements, but here's one from Mr. Avik Kumar. What are the effective methods of ground treatment for the foundation soil of peat or organic soft clay? Oops, this keeps jumping. Having high void ratio, liquid limit PI, etc., and a high amount of secondary consolidation settlement as compared with inorganic soft clay. So I think it's a big question here. The differences between behavior of highly organic clays compared to inorganic soft clays, and I'm afraid it's jumped again. So I've lost it. Hang on. There it is. Can you explain this in a bit more detail? I mean, a lot of what you've been talking about has been discussing that, but I think the big thing here was highly organic versus inorganic soft clays. I think that's the main question there, and differences in treatment and so on.
Well, I guess my first two cases represent the extremes of that. In a fibrous peat is totally organic. There's very, very little to nil of inorganic material in it. And yet it behaves very much like a traditional soil if you use the right parameters. The fibrous peat that I was looking at has a friction angle of around about 26, 27 degrees, and can be considered in the same way that you would consider material that has a friction. It also has a cohesion intercept due to the strength of the fibers, but you need to be very careful about considering that. It's not a cohesion in the traditional sense, although it looks like a cohesion in the Moore-Coulomb equation, but it's a tensile strength. And as you saw, those fibers can break. So in that case, you're really dealing with a material that is more like a very compressible sand in a sense, because you're relying very much on the effective stress to gain strength in the soil, but you're going to get a lot of compression. Those very fibrous peats, as you saw, compress enormously because of very high void ratio, as you pointed out. And reinforcement can allow you to put more fill on for a given pore pressure increase, and therefore allow you to construct faster. It can allow you to overload, which is a way of dealing with the secondary compressions that are associated with these very highly organic materials. When we get to the clays, the traditional clays, like in the Almo test embankment case, there your objective is to make sure that you have enough strength in the reinforcement, enough pull-out resistance that you will achieve the factor of safety at the end of construction. So I'm not sure that I've answered the question, because I'm not quite sure what the question is, but really some of the things you have to deal with are different, but the basic saw mechanics is not all that different.
Yeah, actually, I thought, just as an aside there, what was quite interesting was the that Dutch test embankment, where essentially the fill slides off the end of the reinforcement, which is enormously strong, but not anchored. Yes. So I think that's a really good example of not getting it right, and I'm not thinking about the anchorage. So I like that. I did know about that trial, but I hadn't seen it explained in quite the detail you did. So that was very interesting, learning from these things. Another B-bar question. There was a question. I don't know. Are you familiar with Plaxis? Because someone is asking here. Obviously, a Plaxis user. When you're dealing with soft soil, what's the best model to use? More Coulomb, the HS models, or the soft soil model? I don't know if you have direct experience with that or not.
No, I don't use Plaxis, so I really can't comment on Plaxis.
Okay, let's not worry about that one then. We have another question directly on a project here, which I don't think is very relevant. Actually, this one I do like. This is a very short and simple question, but I've seen people get this wrong. And I'll tell you why, because I've come across cases where contractors are told that someone calculates a settlement, it's going to be 1.5 meters, and they happily measure it. And when they reach 1.5 meters, they stop monitoring. But so how long should you, what length of period of time should you carry out your monitoring of settlement, and what's acceptable as a duration for monitoring settlement on a project? So that's I think a kind of an interesting question.
It's interesting, but without knowing more about the particular situation, it's very difficult to answer, because how long you need to monitor settlements will depend on what is your particular design situation, I think. You certainly need to monitor the settlements, but without knowing what it is you're trying to achieve, it's really impossible to answer the question.
Yeah, no, agreed. Hang on, I've just been given a signal that I think I've been quick read ahead here. I think really your answers have covered pretty much everything. Can you share the presentation? Yes, we'll be asking you to do that. Is anchoring of geotextile important for soft soil reinforcement in order to exert tensile strength? Well, I think you've covered that very well with the results from that Dutch experience. So I think we have the answer on that. So I would say, looking down this now, I think you've really covered pretty well all of those questions. There are a couple more aimed at local project, which you would have no knowledge of. So I've skipped over those. We'll come back to the people who asked those direct later on. But I think to be honest, that is really well covered. I just would like to thank you for myself very much for soft soils is one of those, let's just say, potentially exciting areas of soil mechanics. I mean, you're dealing with things settling a lot, big numbers. It is a very interesting area, and also, of course, one where things can go horribly wrong if you get it wrong. And I think some of the lessons you've given to us today are really good. Yeah, I think I'm going to bring this to an end now. The formal part of the presentation. Kerry, you've got up early today. I don't know if you've had your breakfast yet or not, but
no, not yet. Not yet.
Okay. Well, our organisers are going to bring the event to a close, but they are going to do this little quiz. If you want to hang on and see what goes on, you're most welcome to do that. But anyhow, it'll be the time for me to finish and also bring your interaction to a finish and leave our organisers to look after the rest of it. So, Kerry, just one more time, thank you so much for doing that. It's really been, I said, a little encyclopedia of dealing with the problem of embankments over soft soils using geosynthetics and building up through those 7 important topics. So thanks again. And I will love to hand back now to our organisers and ask Rifa to bring us through to the end of our event today. Thanks, Kerry.
Yeah, thank you, Pak Mike. Once again, thank you, Kerry Rowe, for your excellent presentation. And thank you also to Bapak Mike Dobi for guiding the session. We invite you, ladies and gentlemen, to the upcoming webinar under the theme Mechanically Stabilized Earth Wall, sebuah pengalaman belajar. We're waiting for this slide to come up. Yeah, this is the upcoming webinar under the theme Mechanically Stabilized Earth Wall, sebuah pengalaman belajar. We'll be speaking in this webinar is Professor Insinyur Wijoyo Adiprakoso, MSc, PhD from Universitas Indonesia. And for this upcoming webinar, the presentation will be delivered in Bahasa Indonesia. You can directly register at the link s.id/webinar INA-IGS 05. Once again, you can register right now or later through the link s.id/webinar INA-IGS 05. Next, I would like to invite all of you for the chance to get the very interesting prize, the total of 250,000 rupiah for 2 winners by joining a very short game we have prepared. To give you a disclaimer before we play, everyone who attend this webinar can join this quiz, but for technical reasons, only Indonesian eligible for the prize. So the prize would be 150,000 rupiah for the first winner and 100,000 rupiah for the second winner. But only Indonesian eligible for the prize. But we invite all of you to play along with us. So now you can directly go to your browser on your phone or your PC and type menti.com, MENTI.com, menti.com. And then you have to type the code number shown on your screen right now or also there in the chat box. The code is 98633022. Once again, please go to menti.com through your PC or your mobile phone through the browser and then put the code 98633022. 98633022. Then fill in your name and please make sure it is the name that you submit in the registration for this webinar. So if you forgot what name that you type in when you register, you can easily see the display name of your Zoom right now, what name that you used to actually log in for this webinar. And then later, if you win the quiz, the committee will easily contact you for the prize. Remember, the prize is 150,000 rupiah for the first winner and 100,000 rupiah for the second winner. Everyone is invited to join this quiz, but only Indonesian eligible to win the prize. So you will not want to miss this chance and you will not want to miss this quiz to have fun. So go to menti.com and put the code 98633022 and fill in your name. You can also see the code on your screen and also on the chat box. We will be waiting for more attendees to join. Let's see how many. Right now we have 76 participants to join the quiz. We're still waiting. I will give you some time. Go to menti.com and use the code 98633022. For Indonesian, if it's not clear enough, the code is 98633022. Sekali lagi, 98633022. We are still waiting for more players. Right now, we've reached 80 participants. We're still waiting for others. Go to menti.com, MENTI.com, www.geo-engineering.com and use the code 98633022. Okay, I'm going to count down. We're still waiting for you. Menti.com 98633022. Right now we have 82 players. 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We're going to play now. First question. Answer fast to get the bonus point. When building on saturated fibrous peat, what is the most critical consideration even when you're using reinforcement out of the following? Is it the thickness of the fill material? Is it the thickness of the peat? Or do you limit the filling rate so pore pressure is less than about 1/3 total stress added? You have 35 seconds to answer this question. Answer correct and also answer fast to get bonus point. Only 2 winners, 2 top, the best one, the best 2 of the players can get the total of 250,000 rupiah. 15 seconds. Five, 4, 3, 2, 1. Time's up. Let's see who leads the first leaderboard for the first question. But first, the answer is the third option. Limit filling rate so pore pressure is less than about 1/3 total stress added. 32 answer correct. Let's see. So for the first question, who leads the leaderboard? For the first question, congratulations, Respati, but not yet. We will wait until the third question to see who actually leads and actually win. 2 people will win this quiz. Okay, next question. Question 2 of 3. Let's see, what was the question? Recognizing that all clay soils are rate sensitive to some extent, what is the key characteristic of soil Kerry classified as rate sensitive? Is it plastic limit? Is it pore pressures build up after the end of the construction? Or time-dependent settlement after the end of construction? You have 45 seconds to answer the question, but answer fast to get more points. Is it the first option? Is it the second? Or is it the third option? $20 seconds. Let's see. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Time's up. Let's see. The correct answer is the second option. Pore pressures build up after the end of construction. Let's see who leads for the second question. This is the leaderboard. The fastest one will be Danang Setya, but the one with most points is Dedi Kusman, but not yet. Let's see for the third question. This is going to be accumulated. Who will win? This is the last question, question 3 of 3. Answer fast to get more points. What is an area that pulls together all aspects of what Kerry discussed? Is it column-supported embankments? Is it reinforced soil walls, or is it embankments on peat reinforced with geogrids? Let's see. You have 45 seconds to answer. Is it the first option? Is it the second? Or is it the third? What is an area that pulls together all aspects of what Kerry discussed? Time is ticking. We should be already answered this. All right, 15 seconds to go. 5, 4, 3, 2, 1. Time's up. All right, this is the moment. Oh, wait, sorry. The answer for the third question is the first option, column-supported embankments. Let's see who actually won this quiz. So, oh, what happened to the Kusman and Yudi Ernadi? But let's see. Congratulations to Ray Patman with 2,747 points, and also Danang Setia with 2,703 points. Ray Patman will get 150,000 rupiah, and Danang Setia, as the second winner, will get 100,000 rupiah. Well, that's it for the quiz. Congratulations once again for the winners. The committee will later contact you for the prize details. Ladies and gentlemen, we have now reached the end of the event. Before you leave this webinar, we would like to inform you that you can access your e-certificates and the soft copy material from the speaker by visiting the link s.id/info INA-IGS 04, or you can see on your screen and also on the chat box. After filling the quick survey, you will be redirected to the e-certificates. Once again, you can go to s.id/info INA-IGS 04 on your browser. You can see it on your screen and also on the chat box for the e-certificates and also the info of the material presentation by the speaker. But you can get it after you fill a quick survey from us. Once again, thank you for your participation. We hope we can see you at the next event. At last, good evening and stay healthy, everyone. Thank you.